Okay, hello. This is a video I'm recording which is entitled Everything You Ever Wanted to Know About Area, Volume, and Surface Area. I'm going to go really fast because it's all review, but maybe a little different. Alright, so first we're going to talk about area of basic figures. And the most basic figure we could possibly ask to find the area of is a square. So, how do you find the area of a square? Well, in fact, maybe the most simple object is a square with side length 1. And it's more or less built into the very definition of area that the area of a square of side length 1 is 1. So this is 1 square unit. Okay, great. In fact, we might call that an axiom. I'm going to call this axiom 1. This is the first area axiom. Alright, what else do I know about area? Here is axiom 2. Axiom 2 is congruent figures have the same area. Congruent figures have the same area. So it's a property that the figure has, and if you move that figure to some other location such that it's congruent to the original figure, then they should have the same area. All right. The other thing, the third axiom is I'll just call the partition principle, and the partition principle says that you can, if you need to, take a figure and partition it into a bunch of subfigures, and that the area of the entire figure is the sum of the area of the subfigures. So if you can create non-overlapping regions, then you can just add them up. All right, I claim this is about all I need to prove the area of every single object that I might care about. Well, at this moment I know how to do one thing and one thing only. That is take the area of a unit square. Well, a reasonable question that we might ask now is, how about a square which is not a unit square? How about a square which has side length 3, for example? I think it's a pretty straightforward way to do this, and that is to split it up into unit squares. So I can do this like boom boom. And now what I know is that each of these squares has area 1 by axiom 1, and by the partition principle, the area of this figure is then 9. Okay, that works pretty well as long as you use integers. What if instead I have a square with side length 1/3? This seems a little bit harder, but no, it isn't. What I can do is, well, I'll temporarily call this thing x, and now I will expand. Should have made this picture a lot smaller, I realize now. But it will be nice and beautiful. Well, I now have a big square, which is a 1 by 1 square, and by my first area axiom, this tells me that the area of this square is 1. But these figures can all be proven congruent to each other, and so this argument leads me to the conclusion that that 9 of these figures have area 1, and so x must be 1/9. Alright, and so we have sort of an axiom that says the area of a unit square is side length 1. We have sort of a theorem that says that if a square has a side length of some integer, then it must be just the square of that number. And now, if the square is a unit fraction, well then again, the area of the figure is just the square of that number. I've just proven that the area of the square is 1/9. Alright, and we can just kind of keep going with this. Suppose you give me a square of side length 7/2, for example. Well, if this is 7/2, let's see, what do I do? I can just take this out now. Extend this. Well, that's 7/2. That's also 7/2. And I don't know what the area of the square of side length 7/2 is, but these are all congruent, and so the area of the entire square is 49 by my square theorem. And so 4 of these x's has to be 49, and so x is 49/4, which of course is just 7/2 squared. All right, this basically settles the issue. I can now find the area of any square. Okay, just about. One thing that's left to discuss is what we do if the side of the square is something like √3. And I'm just going to let this one pass in silence because no one really understands irrational numbers anyway. All right, this video is seemingly going to take forever because I have done a bunch of work and I am only at the point of finding the area of a square. All right, let's move on to the area of the next most simple figure, and that is a rectangle. Well, how do we find the area of a rectangle? There are many ways to do this. The probably most simple thing to do is if this is 3 and this is 5, for example, well, I could just split this up, right? But then I sort of have to do all that work over again from the previous section, and I don't want to do that. So this is clearly 15, and that's how you should be thinking about that. But maybe we can do something else. So let's take a rectangle in general where I make no particular assumptions about whether the side lengths are integers or not integers. Can I somehow use the what I've learned about squares to find the area of this figure? I claim I can. This is a pretty interesting argument, and maybe you've never seen this before. Here's what I'm going to do. I'm going to extend side length b by a, and I will extend side length a by b. Something like this. And if I do this, well, I've formed a square, of course. And I have this situation in which, well, this is A, this was also A, this is A, this is A, B, 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 B. So, what are the areas of all these things? Well, this was the original thing which I sought the area of. Let's call that x. By my axiom which says that congruent figures have the same area, well, this is also x. But this is just a square, so by my square theorem, that's a squared, and this is b squared. And now we resort to algebra in some crucial sense. If the area of the entire square is also by the square theorem, it must be a plus b squared. And by the partition principle, the area of the square is also 2x plus a squared plus b squared. And since a squared plus 2ab plus b squared is a squared plus b squared plus 2x, well, that just tells me that ab is x. And so maybe the area of a rectangle is actually like a theorem. All right. Now we're going to go a lot faster. I know how to find the area of a square. I know how to find the area of a rectangle. Let's find the area of the next simplest object, and that is a right triangle. Well, if I have a right triangle of side lengths A and B, and I don't know what the area of this is, what I can do is I can enclose this right triangle in a rectangle, and then this figure is B, and this is A, and since this is X, well, the area of the entire rectangle is AB, and so 2x is AB, and so it's pretty clear that the area of a right triangle is the base times the height divided by 2. All right, so that settles right triangles. Well, next I'm going to leave aside, I'm going to let alone the other kinds of triangles for a moment and go to parallelograms. And in fact, parallelograms are a little bit subtle. So let's draw some parallelograms. Here's a parallelogram which looks kind of like this. This is the picture you will often see. Okay, these are parallel. Let this be base B, and let the height be h. Well, again, it seems that like what I can do in this case is, well, I can just partition this and move it, right? what I would like to do is draw a box kind of like this. And, well, now I think we see that to the extent that these are also parallel, I can prove that this piece over here, x, which I lose, reappears here. And so the area of this parallelogram is in fact just the same as the area of this rectangle, and the area of this rectangle is b times h. So the area of this parallelogram is bh. That's pretty much fine, except there are some devious parallelograms which do not permit this type of dissection if the parallelogram is extremely slanty. So something like this. Well, then we have a task on our hands. So let's call this h, and let's call this little thing b. All right, how are we going to deal with this parallelogram? I think you see that this method won't work. All right, so I'm going to enclose this whole thing in a box, and I'm going to call temporarily, let's call the area of this right triangle, which we have down here, let's call that A. And let's call the area of the parallelogram, let's call that big B. And then this is also an A over here. Okay, leaving out the proof details. All right, so I would somehow like to determine, maybe it's distracting to call this A, to call this B. Let's just call this capital X. Okay, so this is A, and this is X, and this is A. I would like to argue somehow that the area of X is B times H. Well, I have a B times H rectangle just sitting right here. It's this one. And so while I have this large rectangle which has been partitioned into A, X, and A, what I'm going to do is simultaneously pursue a different partition. And in this different partition, what we have is this green rectangle and a red rectangle. And indeed, what we find is that the red rectangle is composed of an A and another A. Maybe I'll do this. Okay, so what we have is, perhaps it's kind of lame to introduce algebra into this, but what we have is that on the one hand, A plus X plus A exhausts this large rectangle. On the other hand, A plus this green region, which I'll just call question mark, well, in fact, I don't have to call it question mark. The area of this green region is just BH. And so that shows, after all, that the area of this parallelogram is BH. All right, things suddenly get a lot easier now. Once you have solved these kinds of tricky decomposition cases, now suddenly finding the area of things becomes really easy again for a little while. Because, and the chief result which we can now claim is that any triangle whatsoever has a very simple area formula to it. If this is B and this is H, well, any triangle that I want can be extended via a copy into a parallelogram. And since these two triangles have the same area, and the area of the parallelogram is B times H, then the area of the triangle must be 1/2 BH. And this works even for very, very devious looking triangles. Maybe something like this. Or perhaps, no, not devious enough. Something like this, I guess, is what I'm looking for. Some triangle like that. It's actually not obvious whatsoever that this triangle does have area 1/2 BH. But the answer is it does. Because even this triangle can be extended via a copying into a parallelogram. And I sort of did all the hard work over there to show that the area of this parallelogram is indeed BH. And if the area that the whole parallelogram is BH, then the area of this triangle is 1/2 BH. All right. So we're at about third grade now. You know how to find the area of triangles, parallelograms, rectangles, and squares. I swear this is an advanced video. I promise. What are the other figures perhaps worth mentioning? Well, trapezoids. That seems to be something that people care about. So let's talk about trapezoids. How do you find the area of a trapezoid? Well, if I call this guy B1 and I call this guy B2, and if the height of the trapezoid is h, probably the very simplest thing to do would be to copy B2 up here, copy B1 over here, and if I do that, that's B1, that's B2. The mysterious area of this trapezoid, which I can call X, is over here, and of course, this is now just a parallelogram. And so the area of the parallelogram is B1 plus B2 times H, and so the area of the trapezoid is just half of that. So we get the trapezoid formula. In fact, we don't just get the trapezoid formula, we get the formula for really any polygon whatsoever, because any polygon whatsoever can be decomposed into a bunch of triangles. And there are many, many ways to do this. Of course, you have to give me sufficient information about the polygon, like the measures of all the sides and the measures of all the angles. And perhaps I might need trigonometry, but since every polygon is decomposable into triangles, I will call this situation solved. All right, that goes really well. Things get hard again when we start talking about circles. All right, how do you find the area of a circle? Perhaps first we should talk about this. Well, okay, we have all these properties of a circle. Here's the center, this is the radius. Ooh, that's pretty bad. Here we have a diameter. And we also have the circumference, which we think of as being the entire distance around this thing. All circles are similar, and since all circles are similar to each other, the ratio between the circumference and diameter will always be constant for any circle. That's something worth talking about, but maybe not right now. And we have a name for that constant. We call that constant pi. So by definition, pi is the ratio between the circumference and the diameter of any circle. As you scale the circle up, the diameter increases, but the circumference increases by the same factor. Okay, this is our definition of pi, and so the formula for the circumference of a circle just follows. In fact, well, okay, I'll leave it at that. How do you find the area of a circle? Well, pi doesn't seem to have anything to do with the area at all. In order to find the area of a circle, we cannot proceed as we have done, because you just can't fit the boxes in here. And in fact, no matter how you partition the circle, there are always going to be little curvy bits. And our previous discussions are not going to help us with this, or at least not directly. We need to try something else. So what we need to do is we need to use what I call fake calculus, or baby calculus. We need to fake it. What we need to do is we need to partition the circle up into some things. So I'll just get right to it. What I'm going to do is I'm going to take this circle. I'm going to suppose that it has radius r. And this is not even a very good picture. But what I'll do is I'll partition it up into these wedges. So I have all these wedges. Now these wedges are kind of triangular looking, though they are not actually triangles. But if I take these wedges and I rearrange them in a particular formation, 1, 2, 3, 4, 5, 6, 7. I think I miscounted. 1, 2, 3, 4, 5, 6, 7, 8. What I have is something which resembles a parallelogram, or perhaps just a rectangle. And what is the height of this parallelogram-looking thing? Well, it is more or less, roughly speaking, the radius. And what is the length of the other dimension of this thing? Well, it is more or less half of the circumference. And since the circumference is the pi times the diameter, and the diameter is 2r, then half of the circumference is in fact pi r. If you've never seen this before, it's amazing. What this tells me is that the area of a circle should be approximately pi times r, or pi r squared. Now, this doesn't totally work because these are notch triangles, they're wedges or sectors, and this is does not quite have height r, et cetera, et cetera. But I think you see, here comes the fake calculus part. Fake calculus, well, actually, we're not doing fake calculus yet. At this point, we're still just talking. If instead I choose to split it up into 16 wedges, well, now I'm going to get something which more closely approximates 2, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 16. Okay, well, now the little roundy parts are less roundy. And so this is still going to be approximately r, but it's going to be sort of closer to being r. And this is still going to be 2 pi r, but we're going to have sort of, it's going to progressively get more and more like an actual rectangle. And the fake calculus part is that if we somehow let the number of partitions or the number of wedges approach infinity, then this strange shape is in fact in the limit going to be an actual rectangle whose area is exactly pi r squared. All right, for that reason we say that the area of a circle is pi r squared, and we're pretty happy with that. Good, all right, that was a crash course. How long did that take? 22 minutes. Oh my God, way too long. Hopefully you watched this on 2 times speed. You now know how to find the area of every single object. Coming back in 1 minute to take the volumes of things.